Hi everyone, I'm Haoyu Wang. Today I want to talk about BGP routing policies in ISP networks. And BGP stands for Border Gateway Protocol, and ISP stands for Internet Service Provider. So we firstly want to understand how BGP appeared. So previously, the requirements of the internet was pretty simple, and the routing strategy was mostly shortest path routing. And over the time, as the internet become much more commercial and the ISPs want to make more profits, the broader gateway protocol was invented. But the BGP has some problems. So when BGP was first introduced, it was just pretty simple path vector protocol. But as time goes by, more and more incremental modifications were added, and the increasing mechanisms among in BGP can overlap and conflict with each other, which result in unpredictable problems. So we'd like to address such problems. But why address such problems is challenging. For example, changing the contents of update messages or the way they are propagated can be very hard. So in order to address the problem of BGP, why we want to focus on the decision process BGP uses. So actually, most modifications to the protocol have been made to the decision process BGP uses to choose routines. And the result of this is that the protocol, where most of the complexity is in the decision process and the policies. Therefore, in order to understand BGP, it's necessary to understand this decision process and the policies of ISPs that give rise to the design. What we'd like to cover today, firstly, basic idea of BGP, second, business relationship policy, third, traffic engineering policy, and then policies for scalability, final, security-related policies. Business relation policies arise from the economic or political relationships between ISPs. And the traffic engineering policies come from the need to control traffic flow within an ISP and across peering links to avoid congestion and provide better service quality. And the policies for scalability is to reduce control traffic and avoid overloading routers. And the security-related policies are often used to protect an ISP against attacks. Then we'd like to delve into the basic idea of BGP. So BGP is a routing protocol used to exchange reachability information across autonomous systems. The difference between an ISP and an enterprise network is that ISPs usually have more complex policies based on the fact that they often have several customers and contact to multiple locations. And they have much more complicated traffic engineering goals. And they also run BGP on internal routers, but enterprise network only run BGP on border routers. And then we'd like to discuss what is a BGP decision process. So in order to give ISPs greater control over route selections, several attributes were added to advertisements, allowing a router to manipulate its decision based on the values of such attributes. And the result is that the BGP decision process comes out, consisting an ordered list of attributes across which routes are compared, as shown in this table. the router goes down the list, comparing each attribute in the list across the two routes. If the routes have different values for the attribute, the router chooses the one that has more desirable attribute. Otherwise, it moves on to compare the next attribute in the list. And the route that is chosen is used by the router to forward packets or datagrams. And the policies have such attributes. So root attributes can be divided into three categories. The first one is locally. For example, this local preference is an integer value set and propagated throughout the local autonomy systems and will be filtered before sending to any neighbor. And this neighbor attribute, this neighbor category is the attributes. For example, the MED multi-exist discriminator attribute is a neighbor attribute. It's typically used by two autonomy systems connected by multiple links to indicate which peering links should be used to reach the autonomy system advertising the MED attribute. And if attribute is not local or neighbor, it's neither. Some attributes, for example, is eBGP learn over IBGP learn is whether the route was learned through an external BGP or an internal BGP. And the result of the decision process is the set of equally good border routers for each prefix. And the three steps a router uses to process router advertisement. The first one is import policy. Import policy is applied to determine which routes should be filtered and hence eliminated from consideration and may append or modify attributes. The second one is second step is router applies the decision process to select the most desirable route. And the third one is export policy. And export policy is applied when to determine which neighbor the chosen route will be exported to. And ISP can modify its policies by controlling any of these three steps. And the three classes of knobs that can be used to control import and export policies are listed below. First one, preference influences. The second one, filtering eliminates. And third one, tagging. We will see more specific examples of these three strategies in the following lectures. And to solve the problems of there may be misunderstood between different ISPs, the route map come out. A route map is a language constructed to modify route attributes and define conditions that determine which routes are exported to peers. And it helps different ISPs to communicate with each other. And this is an example of route maps. And then we like to go to the business relationships. So the business relationships, we focus on business relationships because ISPs often wish to control next hop selection so as to reflect agreements or relationships they have with their neighbors. And the three common relationships ISPs have are a customer provider, peer-to-peer, backup relationships. And the two key ways these relationships manifest themselves in the policy. The first one is influencing the decision process. For example, by assigning the local preference. ISPs often prefer customer-learned routines over routines learned from peers, and providers, if both customer and peers are available. And often ISP will achieve this by assigning a non-overlooping range of local preference values to each type of peering relationship. For example, local preference values may be in range 90 to 100 to be used for customer, and maybe 60 to 70 for peers, and 60 to 80 for backup links, and so on. And the second one is by tagging advertisement with a community attribute. So routes learned from providers or peers are usually not exported to other providers or peers because such routes have no economic profit for an ISP. So ISP want to tag in advertisement with a community attribute to signify the business relationship of the session, and filter routes with certain community attributes when exporting routes to peers. And then we want to go to the traffic engineering. Traffic engineering come up because another goal for many ISPs is to engineer their traffic by modifying preference within the same business class to maximize certain performance criteria. For example, to achieve desired quality and availability. And ISP can modify the import policy applied by ISP's routers to achieve traffic engineering. And traffic engineering can be divided into three categories. The first one is outbound traffic control. Second one is inbound traffic control. Another one is remote control. So outbound traffic control affects which routes get in the set of equally so actually some import policies may affect the route get in a set of equally good border routers. And one common goal for traffic engineering is to early exist routing where the ISPs forward traffic to its closest possible exist point, so as to reduce the number of links packets traverse and hence the resulting congestion in its internal network. And another goal is to reduce congestion on outbound links to neighbors, and this can be done by loading balanced traffic over several links. And another one is to achieve a level of load balance, balancing load to make spare capacity on both links equal. And this can be very difficult. The key challenge is to select the proper set of prefixes and change attributes for each appropriately. Selecting too large sets will cause too much traffic to shift, overloading one of the links. So we can solve this problem by using automated tools to predict the effects of these actions. And then we go to inbound traffic control. So ISP's internal congestion may be exacerbated by its neighbors because its neighbors might not be aware of ISP's traffic engineering goals. Internal topology or load on internal links due to previous reasons. But an ISP can convince its neighbors to allow the ISP to control how much traffic it receives on each link from the neighbor. And this can be done by modifying the MED attribute. Also, shifting the traffic between links to different neighbors is very challenging. And an ISP can prepend multiple copies to its autonomy system number to the autonomy system path in order to artificially inflect the AS path length. For example, suppose B wishes to transfer some traffic from its link to A to its link to C. B can do this by appending additional copies of its AS number onto the AS path in BJP advertisement is sent to A. This increases the AS path length in this advertisement, which causes routes advertised by C to other ISPs to become more desirable in comparison. Another one is remote control. In certain cases, an ISP may need to remotely manage a router's configuration to implement a desired policy. And this can be done by changing community attributes. Since our time is limited, I don't want to list any example here. And then let's go to scalability. So some misconfigurations and faults in the neighboring ISPs can lead them to generate excessive risk of updates. And sending updates too frequently can trigger route instability, leading to poor service quality, or even can overload a router's processing capability or memory capacity. And this can cause outages and router failure. A proper configured set of BGP policies can improve the resilience of a network to these problems. And the common goal includes first, limit routing table sizes. Limiting routing table sizes can be done by protection from other ISPs. ISPs can protect themselves from excessive advertisement from neighbors. Second one is protect other ISPs. ISP can reduce the number of profits it advertises by using route aggregation, which instead of advertising to adjacent prefixes. And also another goal is to limit the number of routine changes. So routing instability is undesirable, as it can increase CPU load on routers. And frequent shifting of traffic also can introduce packet loss in applications. And flap dumping is a mechanism that limits propagation of unstable routes. It works by maintaining a penalty value associated with the route that is incremented whenever an update is received. When the penalty value surpasses a configured threshold, the route is the route is suspended for some time. And then we'd like to briefly introduce the security related policy. So ISP may wish to exercise defense programming to protect itself against attacks. And there are three common approaches. The first one is discarding invalid routes. And it can be done by import filtering. ISPs may want to protect their customers from learning individual routes by performing sanity checks to ensure update content are valid before propagating themselves internally. The second one is secure the network instruction, and it can be done by export filtering. So an ISP may wish to prevent external entities from accessing certain internal resources by conferring its export policies that filter BGP advertisements for the destination that shouldn't be externally reachable. And the third one is block denial of service attacks by filtering and dumping. So denial of service attacks can degrade service by overloading the routers with extra BGP update messages or consuming excessive amount of link bandwidth. Lastly, we would like to talk about three key areas of research related to BGP policies. The first one is configuration checking. Second one is language design, and the third one is new architectures. I will provide links to these three specific areas for your interest, but I won't cover them in depth in my lecture. Thank you so much for listening to my lecture. Wish you have a good one.